Ramanujan series for pi. Well, so there was this very brilliant mathematician, Srivanti Ramanujan, who, well, the history says that he used to dream with goddesses from, in his dreams, that will tell him like series like this, or he would be able to come up with this crazy series to find important values in applied mathematics. So this series, just check it out, for n factorial times that linear function over another n factorial to the fourth power. This crazy series. Well, approximating this value, the value of this series, infinitely many terms, is equivalent to find 1 over pi. So that's one of these series that is used to find the value of pi, among many other infinite series. You want to know more about him? Just Google this guy's name, and you will find a lot of information about him. He would be able to also compute big powers of big numbers in seconds in his head, amongst many other things. And well, if also you want to try this series and check the convergence of divergence using the ratio test, well, I think that'll be a good exercise, a good challenge exercise. Well, we're not going to do that one here. It's going to take basically half of a lecture to go. In the meantime, we'd rather go through the root test. Well, the root test, so the criteria for the root test is exactly that of the ratio test. So we're going to compute a limit, and if the limit is less than 1, the series is absolutely convergent. If the limit is greater than 1 or infinity or DNE, the series is divergent, and if the limit is equal to 1, the test is inconclusive. Alright, but what are we going to do this time? So we're not going to find the absolute value of the ratio of the next term to its previous term. No. We're going to take the nth root of the absolute value of the general term. And well, very often time this is a very short type of problem, and this is useful a lot when having n powers. And that's because that n power will cancel out with the nth root. The same way we cancel a second power with a square root, the same way we cancel a third power with a cube root. Well, in this case, the nth power gets canceled with the nth root. All right. So let's look at one example. Actually, a few examples. And well, so what do we? Yes. And this is also another alternative for alternating series test, because here we're taking the absolute value of the expression. That absolute value will cancel those alternating factors, all right? So let's set up the limit here. So that's a limit of the nth root of the absolute value of 2n plus 3 over 3n plus 2 to the n power, absolute value of that, as n approaches infinity. Well, on the one hand, these absolute value bars, we can stop writing them because we don't have any negatives, we don't have any alternating factors, and we can also cancel out the nth root with the nth power. So that's going to be the limit of 2n plus 3 over 3n plus 2 as n approaches infinity. And well, in this case, this limit is a polynomial over polynomial. The degrees match. We can just go with the ratio of the leading coefficients, which in this case is 2/3. All right. So we're done with finding the limit. So now we need to check the criteria for the root test. So in this case, we need to check whether this limit is less than 1, greater than 1, or equal to 1. Well, in this case, 2/3, it's a number less than 1, which means that the series converges by root test. All right, converges by the root test. See, it's a very short test, this one. And it's going to be like this for most of the exercises, you'll see. All right, so let's look at another example. Sigma n equals 1 to infinity of n to the n over 3 to the 1 plus 2n. Notice how this series has a lot of n powers, and this is where the root test is great, because that's going to help us cancel out those n powers by that nth root, right? So let's see. So let's set up a limit of the nth root of the absolute value of n to the n over 3 to the 1 plus 2n as n approaches infinity. Well, so let's see. Again, we don't have any alternating factors at all. So, and in this case, I wouldn't just cancel n with this n. So what I'm going to do is I'm going to rewrite this 3 to the 3 to the 1 plus 2n. I'm going to use properties of exponents or laws of exponents to write that denominator, and then we're going to take the nth root for every single factor. All right, so limit n approaches infinity. So that's going to be the nth root of, oh no, not yet. The nth root, for the whole thing, n to the n over 3 to the first power times 3 to the 2n. So we may now distribute in a way the radical limit n approaches infinity. So that's going to be the nth root of n over the nth root of 3 times the nth root of 3 to the 2n. Alright, so number 1. Oh, actually I forgot 1 power of n here, n to the n. So number 1, in the numerator, we can cancel out this n root with the n power. That's going to leave us only with n. So that's going to be the limit, and that's an n over, well, I'm going to rewrite this nth root of 3 as a 3 to the 1 over n. Again, recall that the index of the radical is the denominator of the rational exponent, and in this case we have an invisible one for the 3 inside of the radical, so that's the numerator. That's an invisible one. Well, it becomes visible when we rewrite it in rational power form. And over here, this will be 3 to the 2n. How about the whole thing to the 1 over n? All right. So we will be able to divide this n with that n, keeping the 2 in there. And that 3 to the second power will become a 9. So what are we going to have? Well, limit n approaches infinity of n over 9 times 3 to the 1 over n. Okay. So we can already evaluate the limit right here. So n in the numerator, well, that's just going to be infinity over 3 times 3 to the 1 over infinity. But I mean, 1 over infinity will be 0. 3 to the 0 is 1. 1 times 9, actually. 1 times 9 is 9, but I mean infinity over 9, that's still going to be infinity. And in this case, well, because we got an infinite limit, this means that the series diverges. Diverges by root test. All right. Let's look at another example. So again, we have, what do we have? Sigma n equals 1 to infinity of n over n plus 1 to the n power. All right. So number 1, let's set up the limit as n approaches infinity of the nth root of the absolute value of n over n plus 1 The whole thing raised to the n power. Well, again, we can get rid of the absolute value bars because we don't have any negative terms, we don't have any alternating factors. And well, at the same time, in this case, we have an only one overall n power, not like the previous example in which we needed to first use laws of exponents to distribute the power so we can individually do the necessary cancellation. In this case, we can cancel the n power with the nth root in one shot. So this will be limit n over n plus 1 as n approaches infinity. Well, what do we have? Polynomial over polynomial. That's and the degrees match as well. That's the ratio of the leading coefficient, which in this case happened to be 1 over 1. But 1 over 1 equals to 1. And well, what does the ratio root test tell us when the limit is 1? It's the same as in the ratio test. It's inconclusive, right? Test inconclusive. In fact, you would have to go through different tests. Maybe try to use the n-term test for divergence. Some other, or no, I don't think the ratio test is going to be a good idea because no, actually it's going to give us the same result. It's going to give us a 1. So we would have to go about another test right here. All right. So when it comes to using the root test, sometimes we will run into limits of this form. Actually, that first limit, I mean the nth root of n, which is the same as saying limit n approaches infinity of n to the 1 over n. Well, in this case, you might remember this type of limits from Calculus 1, for which you had to use the L'Hopital's rule in a weird way, when you have a function raised to another function. It was not one of those indeterminate forms that gave us 0 over 0 or an infinity over infinity. So for example, this one, if we do the direct substitution, that's going to give us the 0 over 1 over infinity, which is 0, I mean the infinity, not 0. So infinity to the 0, which is one of those indeterminate forms. The next limit ln of n to the 1 over n approaches infinity. That's basically the ln of infinity, which is also infinity raised to the 1 over infinity, which is 0. That's again the infinity to the 0 power indeterminate form. And you have to set this limit equal to y and then solve, or rather evaluate the limit on the right hand side, and in the end solve the logarithmic equation to get the limit. And it was kind of a long process. So at this point, when you're in Calculus 2 or when you apply these limits, in a higher level course, it's fine to just, kind of memorize these limits, just know them and use them, because otherwise, what you would have to do in a situation like this is to do some work on the side, compute the limit using the L'Hopital's rule, half a page for every single type of limit or so, and the problem is just going to take forever. So in this case, just use these limits and you're good to go. All right. So let's look at one example that involves using these special limits. Limit, in this case, well, it's k approaches infinity of the kth root of the absolute value. Oh, in this case, careful, we're gonna use the absolute value. That's a negative 2 to the k power ln of k over k to the 10th. Oh, one more limit. This one right here. It's limit a to the 1 over n. So that's any number to the 1 over n. Well, 1 over n, that's 1 over infinity. It's a number, a to the 0 power, and any number to the 0 power, isn't it 1? So these special limits are equal to 1. All right? And we're going to use all three here, pretty much all three here. Almost, not all of them. All right? Well, actually, the third one, we used it in the example before. Okay. So number one, let's break up this negative 2 to the k power as a product of two factors. That is limit and the root of the absolute value of negative 1 to the k, 2 to the k. So in this case we're using lots of exponents, because what do we have here? That this negative 2 is the same as saying negative 1 times positive 2. Both factors raised to the k power, so we essentially distribute the power, and that times ln of k, and we divide this by k to the 10th power. Absolute value, let's close the radical, and in this case, well, we can go ahead and cancel out this alternating factor, and we can get rid of the absolute value bars. And again, that's because this alternating factor outputs negative values and positive values depending on the input that we get, if it's an even or an odd input. And again, those absolute value bars turn those negatives into positives. And well, that's going to leave us with the following: n approaches infinity, limit n approaches infinity of the nth root of 2 to the k, ln of k, and k to the 10th. So let's find out what this limit is. So in this case, I'm going to distribute the nth root to the three factors that we have. That is the 2 in the numerator and the 1 in the denominator. That's a limit. The k, oh, it's not n, this is supposed to be k, and also k here. Alright, so also k here. So the kth root of two to the k, the kth root of ln of k over k to the 10th, the kth root of k to the 10th as k approaches infinity. So a bunch of cancellations are going to occur in here. Number one, we can, on the one hand, cancel out this case right here, and in this case we can just use the special limits, right? Because what's gonna happen here? Well, so I'm going to rewrite the limit in the denominator using this property of radicals. So whenever we have radical, the nth root of x to the n power, that's also the same as the nth root of x, and then the whole thing to the 10th power. Right? That's another way, another equivalent expression to rewrite this radical, which is what I'm going to do here in the denominator. This way you can see the special limit that we are about to use. That's one of the special limits from the box right here. So this is equal to limit, okay, that gets the 2, kth root of ln of k, which is actually this special limit, and that's kth root of k, the whole thing to the 10th power. Alright? So, using the special limits, this special limit equals to 1, this special limit equals also to 1, and well, the limit will be 2 times 1, which is 2, over the denominator, which is 1, that's simply 2. But in this case, since the limit is greater than 1, we say in this case that the series diverges by the root test. Alright? And I think this finishes the section. I think this is the last exercise. Alright guys, by the way, the root test root test is not a topic that we were supposed to cover, so if you have access to the day-by-day schedule, so when it comes to this section, it only says to cover the ratio test, but not the root test. So the reason why I'm covering the root test, well, it's two reasons. Number one, we are ahead of schedule, so we have time to cover it, and I think this is an important topic that, well, this is a topic that you will use in your future, that you may use in your future courses, especially if you are a math major or some kind of math major, or in higher level of mathematics as well. So when you get to those engineering courses in which you need to go back to mathematics as well, so you might need, this tool might be a very, very useful tool. And in fact, I mean, we use it's a tool, it's a test to address a very particular type of series, which in this case series that contain a power n. All right, so there will be, that means there will be no homework on this topic. You won't be tested on this topic in the upcoming exam. Yes, you won't have to even memorize this limit. Just have that information for you in case you need it in the future, in case you need it in future courses. In the meantime, we should go to the next topic, which is power series. Alright, so we are essentially done with all the 10 different tests to check divergence or convergence of a series. And so now we're going to move on to another kind of series, so power series. Well, so what we have done so far is work with series that contain constant term. Notice all these series contain an n, it doesn't contain any variable x, by the way. It contains an n which actually describes the number, whatever number of term in the series, like the first term, the second term, the fifth term, etc., the nth term. All right, infinitely many terms. However, in this section, for the remaining of the chapter, we will work with power series. What are those power series? So those series now will contain an x, will contain the variable x. And check this series, for example, sigma n equals 0 to infinity a sub n, which can be a rule like n plus 1 over 3 over 3 to the n, times x to the n. This time, these functions, or rather this series, contain the variable x. And in the same way, we expand, not just for the general rule, not just for the general term, but we also expand for the power of the variable x. And well, in this case, we can have series that are centered at the origin, like the first case, or centered at a value other than 0, other than the origin. Well, so that's actually the note below. And again, this a sub n, which is a sub 0, a sub 1, a sub 2, a sub 3, a sub n, etc., that's given by the factor that contains only n, which is something that we have already worked throughout the previous, how many sections? Throughout the previous 7 sections, right? And in this case, well, so we're going to look at this power series. But the thing here is that these power series are actually infinite series representations of functions, like the exponential function e to the x. We will see how this e to the x has a series representation in sigma notation. The function sine x also contains a series representation in sigma notation. And so does cosine, and so does the function 1 minus x. This one is a very important series. You'll see how that's going to work out later. Well, it has some sigma representation. Well, what's the purpose of this? Well, you'll see later. In the meantime, let's really define what a series is, or actually, let's work with some examples. So in the same way that we expand a few terms of a sequence at the beginning of this chapter, so let's expand a few series for this power series. So, and the idea is that you will see how is this going to, what are these going to look like. So for n equals to 0, we are going to have the power well, x to the 0 power plus the next term n equals 2 corresponding to n equals to 1. That's x to the first power plus x to the second power plus x to the third power plus goes on forever, right? So we just use these three dots to denote that the series just goes on forever. Well, so if possible, simplify and reduce any like terms or anything, like in this case x to the 0, which is equals to 1, x to the first power, that's just x squared plus x cubed plus etc. Well, notice the answer is a polynomial. So these polynomials will be used later to use, or rather to find approximations of values. So something you might recall from Calculus 1 is a linear approximation. So the linear approximation was used to to estimate the value of the square root of 26, for example. So what did you do back in Calculus 1? Well, you were asked to first find the equation of the tangent line for the function square root of x at x equals 25, which is a number close to that 26, and that number 25 happens to be a perfect square. You came up with the linear approximation or the equation of the tangent line, and you used that linear approximation to approximate the square root of 26. You did the same, for example, for the cube root of 65, for example. Well, you use the cube root function and centered at x equals 64, which is the closest perfect cube to 65. You got the linear approximation and you were able to estimate the value of the cube root of 65. Well, so there was a little issue with the linear approximation. Linear approximations have limitations. For example, if I want to use the linear approximation, the same one I use for the square root of 26, I can't use the same linear approximation to estimate the square root of 50, for example, because the square root of 50, it's already too far away from the actual value. In that case, there's a couple of things that I would have to do. Number one, find a linear approximation at the closest perfect square to 50, which in this case is 49. Or in this case, something that they didn't tell you back in Calculus 1, the other solution is not using the linear approximation, but rather we're going to use not maybe the quadratic approximation, the cubic, the quartic, quintic, etc. That is, add more terms to the approximation, and adding more terms in this case gets closer to the actual value of the function. You will see that we will see that later in both as a picture and as a numerical calculation. So that's why we're getting these polynomials here. So those polynomials will be used later to estimate these values. All right. So in the meantime, let's keep working with expanding more terms of the series for letter B. Notice the alternating factor, that's -1 to the 0 power, that's positive 1. And then times x minus 5 to the 0 power over 0 factorial. And then, well, for n equals to 1, that's a -1 to the first power, that's a -1 minus 5 to the first, or 1 factorial plus 1 times x minus 5 to the second over 2 factorial. And well, if the pattern continues, well, let me do one more. That's going to be minus 1 x minus 5 cubed over 3 factorial. But of course, we're not going to write infinitely many terms, right? To denote this, plus dot dot dot, that indicates that the series goes on forever, infinitely many terms. And so that's, well, this quantity to the 0 power is going to be 1. That x minus 5 to the 0 is 1 times 1 equals 1. And 0 factorial, which is also 1, that's just going to give us a 1. Minus x minus 5, yes. Which one? Right here? So, well, in this case, -1 to the 0 power is 1. Yeah, I was just, instead of writing the whole -1 to the n power, I just did the computation. So that's minus x minus 5 plus x minus 5 squared over 2 factorial, which is 2, minus x minus 5 to the third over 3 factorial, which is 6, plus dot dot dot, just to indicate infinitely many times. Alright? And notice how this series do not contain only values of n, constant factors. They now contain this x variable. Well, what is that variable for? You'll see in a second. All right. So write the power series in sigma notation. Now we're going to do the reverse. They're going to give us a polynomial. We're going to come up with a series sigma notation. So let's start. Sigma n equals, I'm going to start this at 1. We could start it at 0, we could start it at 1, it's fine. So number 1, well, in this case we don't have any alternating terms, so all terms are positive, so no need for a negative 1 to the n or negative 1 to the n plus or minus 1. So we're good. For sure, this is going to have some x, and well, here the real trick is to find or to identify the sequence of terms in the denominator of every single term. So what do we have? X over 1, for example. In this case it's an invisible one, so we have 1, 8, 27, 64. Does that sequence sound familiar to anyone? N cubed, right? That's 1 to the third power, that's 1, 2 to the third power is 8, 3 to the third power is 27, and 4 to the 64 is, 4 to the third power is 64, and of course assuming that this sequence honors the same pattern, so that's n cubed, and well, in this case x to the n, because it's going to work n equals 1, 1, 2, 3, 4, so should work in this case. What about the next one? So number 1, careful because we have an alternating series in this case. We have negative plus, and we also have powers of x minus 5, of x plus 5, not just x. So there's a couple of things to care about. Sigma n equals 1 to infinity, and in this case, well, let's start with an alternating factor, negative 1 to the n. So let's see if that's going to work. So starting at n equals to 1, negative 1 to the first power, that's going to output a negative 1, which in this case, it's going to give us the negative in the first term. So that works. All right, let's work with the general term. So that's going to be, well, notice we have a 1, 2, 3, which in this case, this match actually. This 1 matches with the invisible power 1, this 2 matches with the power 2, this 3 matches with the power 3. So for every single term, I think it's going to be an n in the numerator. And well, n in the denominator, however, n plus what number would give us a 4? 3. And well, what do we have? X plus 5 also to the n power. So that's the sigma representation for this given polynomial, and that's something that we will need to do later in order to come up with a sigma notation series for the exponential function e to the x, the trigonometric function sine and cosine. You'll see how is this going to work. Alright, so power series, what's the whole idea? What's the whole thing about? Well, so we can consider this infinite series as some function f of x, So here is the thing. If we assign a value of x to this power series, there's two possible outcomes right here. Number 1, that series may end up being a convergent series or may end up a divergent series, and that's depending on the input that we give to this x, as a function. Well, so I think this is analogous to finding the domain of a function. It's just, I think it's pretty much the same thing, but we just give it a different name. So for example, like finding the domain of a function, let me make something up. F of x equals 1 over x minus 3. this function f of x equals 1 over x minus 3 is not defined for all values of x. In fact, there is one restricted value. That restricted value in this case, x cannot be equal to 3. So for example, if we do f at, say, f evaluated at 4, well, 4 minus 3, that'll be 1 over 1, which is 1. So the function is defined for f for x equals to 4. Likewise, is it defined for x equals to 5? Well, 5 minus 3 is 2, so that's a 1/2. Alright, that's a 1/2. So it's defined for f for x equals to 4. However, is it defined for 3? See what's going to happen here? 1 over 0, and in this case it's undefined. Alright, so, but I mean, you learned this back in intermediate algebra, right? How to find the domain of a function, well, how to evaluate functions. If your output is an actual number, well, then your function is defined at that value. Otherwise, if you get something weird like 1 over 0, well, that's undefined, right? But in this case, in intermediate algebra or in college algebra or pre-calculus, you learn the different guidelines to find the domain. For example, for rational functions, what you did is to set the denominator equal to 0, solve the polynomial equation, and all those values of x are the values that make the function undefined. For logarithmic functions, what you did in this case is to set the argument, that is the expression inside of the natural log function. You set it greater than 0 and solve the inequality, and that interval of values was the okay input for the logarithmic function. For radical functions of even index, like the square root, the 4th root, the 6th root, etc., you set the whatever is inside of the radicand greater than or equal to 0, solve the inequality, and whatever those values are in the interval, those are the okay inputs for the radical function. So what I'm trying to say, you had guidelines to find the domain of a function depending on what kind of function you were dealing with. You didn't do this by just plugging in a lot of infinitely many values on a function to exhaust, because that's simply not how it works. Now, how is this related to power series? Well, let's consider the function f of x equals sigma n equals 1 to infinity. Well, let me do n equals to 0 instead. And let me call this x over 3 to the n. Alright? So, does that series on the right hand side look familiar to some special kind of series? And if so, which one is it? It looks like a geometric series. However, one of the numbers inside of the parentheses in our R, it's x. So this means that we can evaluate this function, let's say f of 1. So that means n equals 0 to infinity. That's 1/3. Well, what would you say about this series when we evaluate at 1? Will this give us a convergent or a divergent series? It's a convergent series because r is less than 1. So this is a convergent. Alright, in a similar way that we evaluated the function at 4 and it gave us an actual value, it was defined. So in this case, for the power series, we are evaluating that series at 1 and it's outputting a convergent series. What about, I don't know, f evaluated at 2? So n evaluated at 2. So what's the output at x equals to 2 for this power series? Is it a divergent series or is it a convergent series? It's convergent, right? Because 2/3 it's still under 1, right? So convergent. In a very similar way that we evaluated the previous function, at 5 it gave us a value, whatever value it is, whether it's a fraction, an integer, a decimal, I don't care, as long as it is a valid value. I mean, it's going to be convergent. However, what if I evaluate this function f of x at let's say at 4? What's the output this time? It's a divergent geometric series, right? And so this is, well, so given a power series, do we really have the time to plug in every single value of x to determine, to exhaust, to determine whether they converge or diverge? So there has to be an actual procedure to find the interval of values or the settable values of x that will output a convergent series, and that is called the interval of convergence. That interval of values, so you will choose any value containing that interval that will output convergent series. That's what the intervals of convergence is. And well, it's described here in the next page. However, what about this? How does that work? We're going to learn that next time when we meet on Wednesday.